All right, everyone. So today we're going to learn about motion in vertical circles, and it's kind of some fun stuff. I like vertical circles; they're more interesting. Some of the effects that you get with vertical circular motion is a little more interesting. Before we get started, though, I do want to point out there is a new Quest assignment. It's called Uniform Circular Motion and Vertical Circular Motion. This assignment will be counted as a major grade. It will be essentially our test. There's no formal test over this unit. It's kind of a shorter unit. And just with the week lost because of Thanksgiving break, which they counted as part of the 6 weeks, and the week lost at the beginning, I'm looking at my pacing, and I want to make sure we have time at the end of the year to review before the exam. So this is one way. Because this is one of the shorter units, I'm just going to go ahead and make this Quest assignment a major grade, and you will have the one free try option on it, unlike the last one, because it is kind of long, but we will have plenty of time in class. Well, we'll have significant time in class to work on it. That's what we'll be doing tomorrow. Okay? All right. There is one question or two involving gravity and orbits because it is essentially an summative assessment. Is that what they call it? Yeah. All right. So with that out of the way, let's talk about vertical circular motion. So up until now, we've been talking about horizontal circular motion. Kind of like that. Well, it doesn't have to be horizontal, but as soon as you start going vertical, then gravity starts playing a part, right? If I go in a circle like this, yes, gravity's playing a part, but it's not changing its motion in the vertical direction, and so it maintains circular motion in the horizontal plane, right? It maintains the circular motion at constant speed. As soon as I start going like this, it's no longer constant speed, okay? And we can get a nice visual for that. I don't know why I pulled this down. Get a nice visual of that from the simulation. Zoom in real quick for the folks at home. So here to start with, I got this object on the rope.
Jingle bell, jingle bell.
Say hi, Mr. McCandless.
It is the 12 days of Christmas giveaways. So teachers, if you hear the jingle bells, the first winner on the 12 days is Sharon Baskerville. Come on down and get your prize in the front office. Congratulations. Another winner tomorrow. Happy Thursday.
Thanks, Mr. McCandless. Oh, no, they don't. No, they do write emails. They write a lot of emails. Anyway. So with Algodo, it's kind of neat because I can turn off gravity. So I've turned off gravity here. Pay no attention to that 14 meters per second because that goes away. But here I got circular motion. This is uniform circular motion. And there are limitations to the program, so the speed is kind of changing. But if I look up here, the speed is pretty much 13.1 meters per second the entire time. And that's because this is uniform circular motion. There's no gravity. Okay. As soon as I turn on the gravitational force, things change. Right? At the top, it's moving about 11 meters per second. And at the bottom, it's moving about 16 meters per second. This is what we would expect, right? If I was to take this ball and whirl it around in a circle, right? And this is pretty heavy. This is like bowling ball material. At the bottom, I feel it a lot heavier than I do at the top. It's moving a lot faster at the bottom, right? Can we conceptually just kind of understand that? When it gets to the bottom, it's pulling down on my hand. When it gets to the top, it's not pulling up on my hand so much, right? If I did it fast enough, it would be pulling up on my hand, but just at these normal speeds, it's pulling down pretty hard there, but it's pretty weak pulling up there. It's also moving faster at the bottom than it is at the top. Why is that? Well, as it's falling, we have a centripetal force from the tension, but I also have the weight force that always points straight down. So that weight force causes it to accelerate and speed up on the way down, and then on the way back up, the weight force still points down, so it's opposing the direction of motion, so it causes it to slow down on the way up. Okay? Kind of makes sense? So,
Does that mean that the tension force is constantly changing too?
yes, absolutely. And that's what we're going to get to right now. So, let me go back to where I turned on gravity. Okay, so, and I'll do the forces. So let me show you what the forces are before. That's an excellent question, by the way. Before, it's a vertical circle. Let me Maybe go down a little bit. Let's slow things up. Again, there's some limitations to this program, so it's not pointing exactly towards the center, and that's because the rope here has some give and it has some stretchiness and it kind of messes things up. But it's pretty much towards the center of the circle, right? And it's pretty much constant, right? It's about 58.6 newtons the entire time. But then as soon as I turn on gravity, and what I'm going to do here is actually increase the force vector size so we can actually see the weight force and the tension force. Okay. Maybe not by quite that much. And so now that tension force is most definitely changing, right? And literally because when it's at the bottom it's pulling down on my hand so hard, that means it's pulling up on the ball a lot harder than it is at the top. That's because the tension force is at a much higher value at the bottom than it is at the top. And if I look at the net force, what you'll see is that the net force doesn't point towards the center of the circle. This one doesn't. Because say at that point there, I have a downward weight force and I have a rightward tension force. The tension force is the centripetal force. But this mg is not pointing towards the center. That's why this is not uniform circular motion. Mg doesn't point towards the center. But if I wanted to add those two force vectors together to get to the net force, I take mg, I put it there, line them up tip to tail, draw my resultant vector from the tail of the first to the tip of the last, and that's the direction of my net force. And it doesn't point towards the center. Okay. Again, why this isn't uniform circular motion. There are, though, 2 times at which the net force does point exactly towards the center of the circle. What 2 times in this motion does the net force point pretty much towards the center of the circle? The top and the bottom, right? At the very top, points right towards the center of the circle. At the very bottom, no other point. No other point. At the very bottom, that's close enough. At the very bottom, it does point exactly towards the center of the circle. So in a vertical circle, at 2 points in the motion, the net force is centripetal. And for those 2 instances, we can use the centripetal force equation that we derive from Newton's second law. Okay? So that's the whole point here. So let me show you what that looks like. Too many things to juggle. I'm trying to record this for folks at home. Okay. So let's talk about just the top of the arc at first. So at the very top, we're going to talk about those 2 instances where we can actually apply Newton's second law for centripetal motion. At the top of the arc, let's do that one first. So at the top of the arc, I have 2 forces, and I need to put them both on my free body diagram. My 2 forces are force of gravity, mg, and the force of tension. Thank you. I have 2 forces pointing down. And remember that centripetal means center seeking. So anytime you're dealing with equations, you're setting up your equations, just call the center seeking forces positive. And then forces that point away from the circle, call them negative. If they're pointing towards the center, no matter where they are, just call them positive. It works, and it makes your life much easier if you just use that convention. So these 2 forces in this case, I would then consider to be positive. Okay? So let's apply Newton's second law. Net force is equal to the mass times the acceleration. I want to be super nitpicky here. If I want to talk about the vector nature of everything, the net force points down, so the acceleration must also point down. And at the very top, what? And it's also in circular motion. So at the very top, just at the very top though, and at the very bottom, I can put little subscript c's there. Now there is centripetal motion still when it's not at the top or the bottom, but the net force is not centripetal, right? Only the tension force would be. Okay, so this is the case. Now the net centripetal force here is the combination of both of these, and since they both point towards the center, I just add them together. The tension force plus the weight force mg equals, and 99 times out of 100, maybe not quite that many, but 95 times out of 100, we make this substitution when we're dealing with vertical circles. The speed squared over r. And again, the speed changes. The tension force changes, but at the very top, I can make the substitution for that instant when it's at the very top. And you might be wondering, well, why? What's so important about the very top and the very bottom? Well, there's some implications that we'll learn about later today, where it's like really what we're interested in and what happens at the very top or what happens at the very bottom. So then I can write mv squared over the radius of the circle. Here's my radius of the circle. This one is done. Oh, much nicer. There's my radius. So this is an equation that we can write for an object moving in a vertical circle when it's at the very top of its motion. Okay? So I'm going to put a little subscript top here on the speed there because I'm going to relate that to the speed whenever we talk about what goes on at the bottom. So at the bottom of the circular arc, string. What does my free body diagram look like?
You have the force of tension pointing towards the center, and then the force of gravity pointing down.
So force of gravity pointing down, and it's the same as this one, right? The object's mass didn't change, so its weight didn't change. The tension, which way is the acceleration pointing at this point? The at this point, at the very bottom. What's that? The center. It's centripetal, right? The acceleration is centripetal, so I'm going to just kind of indicate that here. Just to show you why the tension must be larger than the weight force. Because if the acceleration points towards the center of the circle, according to Newton's second law, the net force must also point towards the center of the circle, which means that the tension force must be larger than the weight force in order for that to happen, right? Make sense? I know it's weird when we start moving in arcs, circular arcs, curved paths, but this still means the same thing. Newton's second law is very powerful tool. It always applies unless you're moving at relativistic speeds, which we don't deal with in this class. All right, and then we just apply Newton's second law again. Net force, mass times acceleration. They are vectors that point in the same direction, the net force and the acceleration. And at the bottom, they are centripetal. These 2 points, at the top and at the bottom, are the only 2 points in a vertical circle where the acceleration and the net force will be entirely centripetal. So what would I write for the net force here? Ft minus mg. Tension force minus mg. And then I make this substitution again. mv squared over r. This is the speed at the bottom. Now hopefully, intuitively, the speed at the top is what? Larger than or smaller than the speed at the bottom? Smaller. And we know that because when it's over here, so let's say it's moving counterclockwise, when it's here, the tension's pulling it towards the center, but the weight force is pulling it down. So the weight force is going to cause it to accelerate. The gravitational force causes it to accelerate. It's like it's falling. It's just falling in an arc. And then as it moves up on the other side, gravitational force still points down, so it's going to slow down on its way up. So we expect the speed at the top to be less than the speed at the bottom. Not only that, to be consistent here, what about the tension? If I want to calculate the tension here, I got to subtract mg from both sides, right? So if I calculate the tension at the top, I get mv squared, where that is the velocity at the top, minus mg. I want to solve for the tension at the bottom, I add mg to both sides. So I get the tension is the mass times the speed at the bottom squared divided by r plus mg. So not only is the tension at the bottom larger than it is at the top, it's significantly larger. And that's because, first of all, the speed at the bottom is a larger value than the speed at the top alone. Then that gets squared. When you square things, it gets even more important. And then not only that, this larger number then gets the weight force added to it. Over here, this smaller number gets the weight force, the same weight force subtracted from it, right? So this tells you that the tension at the top is most definitely larger than the tension at the bottom. And when you have something small like this, that difference might not be that much, right? It's noticeable, but it's not that much. But then you get something heavy, and you start swinging this around. At the top, it's not much pain. At the bottom, it's pulling on my hand. I got it wrapped around my hand. I do this enough times, it'll like put creases in my hand. My hand will start getting red. It's significantly higher tension at the bottom than at the top. Okay.
Wait, why did you? Isn't that sign supposed to be flipped then?
What are you talking about? Sorry about that. I blame that on Brock. Come on, Brock. Thank you. That would have been embarrassing. I guess it was embarrassing. All right. So any questions about that? If you have a vertical circle, again, in this class, you want to conceptually understand what's going on at the sides. But really, especially for computational purposes, really it's what happens at the top and the bottom that's important. Okay. And just to drive the point home, I'm going to bring that simulation back up. Okay. So the net force at all other times doesn't point towards the center. The center of the circle is right here. So I got the tension that does point towards the center of the circle, that's the centripetal force. But then I also have the weight force that doesn't point towards the center, right? So the net force doesn't point towards the center. So the net acceleration also does not point towards the center. Okay? The net acceleration is not pointing towards the center. That's why it's not uniform circular motion. If the net acceleration pointed towards the center, necessarily it would have to be traveling at a constant speed. Okay? Make sense?
Kind of like a planets or something, right? They have circles because gravity.
Yeah, but remember planets actually orbit in ellipses. But yeah, if you had a perfectly circular orbit.
If you have a big enough difference, it
Yeah. Okay. Oh, let me just. Oh, this is good. Okay. What if I don't go fast enough to get through the loop?
Then you go back down.
Oh, wait. I forgot to turn on gravity. If I don't travel fast enough to get through the loop, it becomes a projectile. Right? As soon as something happens, it then becomes a projectile. What happens to make it become a projectile? It wasn't a projectile before, but then it becomes a projectile when there's no tension in the rope. When the tension becomes zero. And so here I can kind of approximate where that happens. Oop, let me slow down a little bit. Happens right about there. Right. No more tension, and now the object moves as a projectile in a parabolic arc. Make sense? So it turns out there's a way. Now what happened? Literally what happened? What Kurt said is very true, and you got to pound this into your gray matter. When the tension becomes zero, it's now not moving in centripetal motion. Remember, the tension is the centripetal force. So if the tension goes slack, there's no more tension force. There's no more centripetal force. It's no longer moving in a circle. It will then move in a parabola due to the gravitational force. So what we can do is actually figure out, and I figured out what speed I needed at the bottom here. It's 13.8. Because it turns out that for any circular motion, we can actually calculate exactly what the minimum speed is required at the top in order to get through the loop. The minimum speed. And any less than that speed, and we don't make it through the loop. And so this isn't the minimum speed. This is the speed I give it at the bottom. But that corresponds with the minimum speed because it'll slow down on the way up. But this speed will correspond with the minimum speed required to get through the loop when it gets to the top. And so as Kurt pointed out, if we look at the tension force, and let's just look at the tension force. Oh, what did I just do? What did Kyle just do? Forces.
Mouse over here.
Let's get rid of the tension force. Make the force. So the tension force is still there. I just took the vector off. And so we can see. Wait, why did I do that? Oh my gosh. Don't listen to me. I got sidetracked. I'm sorry. Got ahead of myself. I blame Kurt. What's going on? Oh, the gravity's off again. Oh my gosh. Oh my gosh. Sorry. Okay, so this is the minimum speed, I think. If I did this right. Yes. So this is the speed I need at the bottom in order to have the minimum speed required to get through the loop. And so if we watch this, watch what happens to the tension. I didn't want to take the tension off. I wanted to leave the tension on and then take the gravitational force, the weight force off. So the minimum speed to get through the top happens whenever at the very top the tension becomes 0, essentially, right? It's almost 0. I didn't do it perfectly, right? But at the very top, if the tension becomes 0, an instant later, right, the object still wants to move in a straight line according to the law of inertia, Newton's first law. Yes, the gravitational force is pulling down on it, wanting to make it move in a parabolic arc. But I'll tell you right now, if this guy was moving in a parabola as a projectile, he would come out here. The circular arc is going to be tighter, right? The circular arc is going to be tighter. So the object wants to move like a projectile because it has inertia, and then the rope will re-engage after it gets through the top. So it's like it goes slack at that instant at the very top, and then it re-engages to pull it back into the circular motion. Does that kind of make sense? So what we see is on the way up, it slows down, the tension goes down, tension goes down, tension goes down. At the very top, the tension becomes 0 at that instant in time, and then as it moves, as it keeps moving, the tension re-engages and starts pulling it back into the circular arc. But if I have less than that minimum speed, then this happens, it goes slack not at the very top for just an instant, but it happens before I get to the top, and the tension will not re-engage because it won't be moving fast enough to stay inside or to want to go outside of the circle. So let me give it a little faster speed. No, slower speed. What am I talking about? A little slower speed, and it goes slack before it gets to the top, and like Kurt pointed out, it ends up falling. Okay. So let's talk about. Oh my gosh, that keeps happening. Let's talk about how we can calculate that minimum speed. And again, I mean the minimum speed required to get through the top of the loop. If I have bigger than that speed at the top, I'm fine. I get through it. But if I have less than that speed, that's the critical speed. The critical speed, if I have less than that speed, then I will definitely fall. So I have this equation. I have that the tension force is equal, or plus the weight force, is equal to mv squared over r. And again, I just want to reiterate, this isn't a class where you just memorize stuff and regurgitate it. You actually have to use your brain, and you have to really critically think and impose conditions and understand what imposing those conditions does to the equations. And so we need to recognize that at the minimum speed, what happens to the equation? The minimum speed to get through the top of the loop, what happens to this equation? What? When this becomes the minimum speed to get through the top, the tension becomes 0. Good, Alex. The tension becomes 0. So here I make the connection. Well, at the minimum speed, we saw that when it had that minimum speed right at the top, the tension became 0 for that instant. So the force of tension approaches and essentially becomes 0. And so I can impose that on the equation, and it actually simplifies a little bit, right? And if there's no tension, then everybody brought what? Everyone brought mass to the party. So you can divide both sides by mass. And then we get a nice simple equation. Acceleration due to gravity is the minimum speed now squared. And again, this is the minimum speed if and only if the tension becomes 0. Right? At the top. You know, emphasizing at the top. Divided by R. Can we all solve that for V min in our head? Square root of RG. Multiply both sides by R. Numerator R, denominator R. Square root both sides. We got V min equals the square root of RG. Notice it doesn't matter the mass. The mass doesn't matter. So if I have this radius loop with this little guy, and I want to get to that minimum speed, which is like, right, you can feel it, right? You can feel it when it goes slack. That's like if you ever go through a loop in a roller coaster where it's kind of sluggish at the very top. You don't completely come out of your seat, but you feel lighter and lighter and lighter until at the very top you kind of come out of your seat a little bit, but then you get pushed right back in your seat as it continues a circular arc. It's like that kind of thing. So at the minimum speed, the tension becomes 0, and I can kind of feel where that is, and it has a certain speed at that point. Well, if I do the same thing with this guy, with the same radius, in a circle of the same radius, it's going to have that same minimum speed. Because all it depends on is the radius of the circle, so I'd have to be careful with that, and the acceleration due to gravity, which usually doesn't change much. Make sense? Now, why do we need to know that minimum speed? Again, if you get less than that minimum speed, this is the minimum speed to get through the top of the arc. So if that minimum speed is not achieved by the time you get to the top, you don't get to the top. The tension goes slack, and you end up falling. Right? If you have more than that speed, then you get through the loop just fine. If you're in a roller coaster and you have more than the minimum speed, which you always do because they design roller coasters so that they don't start a loop and then come back, then you just go through it fine. Right? You go through that loop fine. Speaking of loops, I made this little. Actually, I was about to say, yeah. When is it very important to know that we got that minimum speed and actually more than that minimum speed to get through a loop? Well, if you're a crazy guy like this person, this applies to skateboarding too. If anyone in here is a skateboarder, has anyone done a loop? You've done a loop? Oh wow! This is the first student I ever had that did a loop. Did you practice with them like pushing the mattresses underneath you? Yeah. Yeah, that I wouldn't do it. that's cool though, man. So you know this already. So here's a guy that this is a larger loop, but same general idea. Wait, don't they build roads like that?
Whenever you want to get on the highway, instead of just getting on the highway like one of those ramps,
You do a loop?
why don't you loop on it? Make a jump. Yeah, do a jump off of the loop.
You should become a civil engineer and start designing
It
those.
could solve our traffic problem
Oh yeah, that wouldn't cause any other problems either.
No, I think it's
No.
fine. It just causes more road space. We get more mileage.
So, obviously, you need to have. I'll tell you right now. There's engineers and there's physicists. Maybe not physicists, but someone with an engineering background or just someone that knows physics. When they're designing this thing, they're like, okay, this loop has a certain radius. This is the speed that you need to have at the top. From that speed, you can work out what speed you need to have at the bottom in order to get to that speed, and then you would definitely exceed that speed so that you have wiggle room, right? And so you know that they did that, so he knew exactly what had to be on his speedometer before he started the loop. Because you mess up there, you mess up when you do a skateboarding loop, and you can really get hurt. You mess up when you're doing this loop, and you probably, unless you got a lot of safety equipment in the car, but it's not going to be good.
They probably had some.
Yeah, but that was a tall loop. That would be very
I'm
dangerous.
sure, like,
Very dangerous.
I'm sure they pretty fast.
So what force? There's no string here. And the weight force is not only centripetal at the very bottom, at the very top. What's the centripetal force for the car going through the loop? What's the centripetal force for her going through the skateboarding loop? It's the normal force. Yeah.
That's why you can run. There's like this one big band of loop.
Yeah.
It's like run.
Oh yeah, yeah.
That was really cool.
Yeah, I do that all the time.
Oh, I know.
So yeah, it's the normal force is the centripetal force here. It's the normal force. And even at the top, the normal force points down. The normal force points down. The normal force is exerted by a surface onto the object, and it's always a push, so it always pushes away. This is why when you go through a loop in the roller coaster, when you're going in a loop, when you're about to go in a loop and you start, you get pushed down into your seat because the normal force has to increase to start pushing you through the loop. And if you go through a loop fast, even at the top of the loop, you still feel like you're being pushed down, even though it's up, into your seat. That's because there's a normal force still acting on you. And the normal force is your apparent weight, your sensation of your weight, right?
So you can fake down.
Yeah. We'll talk about that a little bit.
Oh, yeah.
Okay. If you take Physics C next year, we'll talk about it a lot.
Well, I'm leaving.
Oh.
College.
Well, that's sad.
Well, I'll take college.
Okay. So I did make a little simulation for that one too, the loop. So before he goes through the loop, when you're just moving along like that, you got a normal force and you got a weight force, right? And they're equal because he's not accelerating vertically. But the instant that he starts moving in a circle, bam, the normal force goes up significantly because that force is required in order to get through the circle. That force points towards the center, right? And then on the way up, it gets reduced. Ignore the little spikes there. This is the limitations of the program. And at the top, it's definitely smaller than it was at the bottom. Right? But again, if I don't have the speed necessary to get through the loop, then you're going to have a bad day. You don't have enough speed, oh, the normal force becomes zero. Oh, the normal force never became zero because he didn't even have enough speed to get there. So let's go down to, what was it? The minimum speed we need is 14, so about 13. 12.5. So normal force becomes zero right about there. Normal force becomes zero literally means you've broken contact with the surface. And then they have to push mattresses underneath you whenever you hit the ground. Yeah. Cool. All right. Does that make sense? So, let me just describe the types of problems you kind of see with regard to this stuff. Because a lot of circular motion problems aren't actually full circular motion, vertical circles. A lot of it's like roller coasters going over humps or down below humps, right? So let's say you have something like this, where these are circular arcs. They could be roadways, they could be roller coasters. Pretend those are circles. And so they have radii. So when you go down here, when you're driving down here, think of a roller coaster going through a thing. You feel heavier, right? You feel like you're being pushed down into your seat. And that's because you're accelerating towards the center of the circle. So the normal force that acts on you here must exceed your weight force. Just like on an elevator, normal force must exceed your weight force to push you up, to accelerate you up. The normal force here must be larger than your weight force. When I go over the top here, my weight force points down. Same weight force is here, but now I'm accelerating towards the center of the circle, which is down, which means the normal force must actually become smaller. And if I go fast enough, what happens to that normal force? It becomes 0. And that's when you come out of your seat on the roller coaster, when you go over a hump. Right? And then if you go faster than the minimum speed required to do that, which we solved for just like in the other case, then you come out of your seat before you get to the top of the thing. And if this is a car on a roadway that goes in a circular arc, that's when the car jumps up off the ground, right? When the normal force becomes 0, you are literally no longer in contact with the ground. You have come off the ground. Now the difference in this kind of a problem, let's focus on this guy right here, is now the net force points down, but unlike here, the net force points down, but we have forces in different directions. So when we did our net force, centripetal force is mass times centripetal acceleration. Notice I'm just talking about the top and the bottom. I would have mg minus the normal force equals mv squared over r. Cool beans? I forgot to zoom out. All right. Same thing in jet pilots. When you're flying in circular arcs, same thing. Right, if you want to do a loop, as a jet pilot, you do it just like this. The jet pilot himself or herself has a force pointing down, their weight force pointing down, but then it would be the normal force from their seat pushing up. And if you're in a jet, like a military jet, that normal force can get huge, right? It can get 7, 8, 9 times your weight force. And at that point, you're pulling 7, 8, 9 Gs. And I think the average person can only handle like 7 or 8 before they pass out. Maybe not even that much. Okay, I know the jet pilots, they're trained. They can to 9, yeah. Now at 9 Gs, they're wearing those suits that actually constrict their extremities to keep the blood from draining out of their brains and making them pass out. Yeah, that's nuts. That'd be so much fun though. Oh my gosh, if I could do it again, I'd be a jet pilot. Okay. Speaking of planes, one of my favorite movies, and it's a movie based on a real story, an actual story, one of the most harrowing, interesting, scary situations ever to happen to anyone. It's Apollo 13. Where'd you watch it? Oh, you did? Cool. I used to teach that class. I would like to still teach that class. You didn't see that. So, circular motion. If you want to aim this at something, when do you have to let go? At the bottom. Yeah, like I just did on accident. You ever heard of slingers? Right? David and Goliath, everyone knows that story. Right? David slew Goliath with a stone from a sling. That wasn't just David's thing. Like, they used to have military units, like whole units of slingers, just like archers. And they would sling rocks that were just as devastating as arrows. Like, you get hit by a rock that's thrown by someone that swings it around with a sling. And they were good, too. Like, a good slinger would be able to hit a target just like an archer would. It's nuts. So, yeah, I did that on purpose just to bring that up. Yeah. What?
Could you imagine dying to a rock?
No, it happened a lot. It happened a lot, and you didn't even see it coming.
I mean, a lot of people die into a rock, right?
I'd rather get shot with an arrow than hit with a rock.
Even arrows like have rocks on top of it.
Okay, let's keep going. Because, back to Apollo 13. So Apollo 13, it's the story of a spacecraft in one of the early moon missions. Wasn't the first, but it was one of the early ones. And on the way to the moon, where you can't be helped by anyone, like physically, everything starts going wrong. Everything starts going wrong. Like, they're losing oxygen, they're losing pressure. Everything that could go wrong and not kill them was going wrong, and it was going to kill them. And so this movie just shows what they had to go through to, and it's pretty historically accurate. Obviously, it's dramatized a little bit because it's Hollywood, but yeah, they like had to fashion their own CO2 scrubbers out of like rubber gloves and
Yeah, they had
and
the people in the mission control.
yeah,
They had to figure that out. Like,
yeah, they made them.
like a big thing that they had, and they had to fit it in like a 1 foot.
Yeah, it was amazing. It's an amazing story, and it's a great movie that depicts the story with some of my favorite actors. Kevin Bacon's in it, Bill Paxton's in it, Gary Sinise is in it. Excellent actors. Just a great movie. Tom Hanks is in it, right? Yeah. Great movie. And what's cool is it's in the early 90s. It's made in the early 90s, and so you'd think that because they're in space, so they're weightless or apparently weightless, and you watch this movie and you're like, is that CG? Are they using strings? Because man, it looks super realistic, better than any artificial way that you can actually create zero G in a movie today. And it's because those scenes were filmed while they were apparently weightless, literally when they're in zero gravity, but not zero gravity, just apparent zero gravity. And they didn't send them to space to do it, because if you send them to space, that costs a lot of money. I think it's something like, this is a kilogram right here. I think it's something like 10 grand per kilogram to put something into space.
They probably would have
Event maybe. It's real expensive to get stuff to space.
If we make
We're running out of time. So the thing is, so they filmed those scenes here on the Earth. But when they filmed them in a plane that's owned by NASA, and it's got a funny name. Here, I'll play it's a short clip here.
it'd be fun to do.
This is them messing around, getting used to how they were going to film the weightless scenes.
So fun.
So the following footage was shot on the NASA KC-135, aka the Vomit Comet,
I remember that, yeah.
as a test for the movie Apollo 13. This is Bill Paxton and Kevin Bacon. R.I.P. Bill Paxton. That was pretty recent. That was a sad day. And look, they get it wrong though. Playing catch with a football in zero gravity. It's not zero gravity. They're just in free fall. All right, so now watch though, because look, they start on the ground and then they just seem to magically start floating up there, and now they're floating. This is just in a plane on the Earth. And then after a little bit of time, they are now no longer floating. And then a little bit later, they're sitting there, and then they just start floating. And the football moves in a straight line when you throw it. You can ride on this. They sell rides on it at sometimes, I think. Probably not right now, but it's like a few grand or something. And you gotta travel to where it is, I think.
They have multiple players.
It's Kevin Bacon. He's in Tremors. If you never saw Tremors, that's a great movie too. Anyway, so that's the Vomit Comet. So how does the Vomit Comet work? Works the same way that we've been talking about. You get the plane to fly in a circular arc. Now, it's not exactly a circular arc. It's a little more complicated. But to relate it to what we're learning, let's just assume that the plane flies in a circular arc. And then you find, so here's Bill Paxton. So if he doesn't come off the floor, as they're flying in this arc, he's got a normal force on him. And then he's got a weight force on him. And the weight force must be larger because he, along with the plane, is moving in a circle, right? Now there will be some, and so if I write the equation here, I get mg minus the normal force equals mv squared over r, where radius is just the radius of curvature of the plane's arc. Now, if the plane flies fast enough, then the normal force gets small enough, and once it becomes zero, he just leaves the surface. He breaks contact with the floor of the plane. If he reaches that speed at the very top, then that would be the minimum speed required at the very top in order to come off the ground at that instant. But if I'm faster than that by the time I get to the top, well, the normal force has become 0 before I got there. Right? So again, I make the condition, or I impose the condition. I'm talking about the minimum speed. When I impose that condition on the mathematics, I'm implying that the normal force becomes 0. And that's why it didn't matter if you were Kevin Bacon or Bill Paxton or Tom Hanks or Gary Sinise. Doesn't matter. All different masses. Masses don't matter. Right? And so we end up with that minimum speed that the Vomit Comet must travel at is still the square root of RG. And then they exceed that speed quite a bit as they fly in the circular arc, so that instead of just becoming weightless for an instant at the very top, we become weightless before we get to the top, and we're weightless till after. So when you watch that movie, realize all of those weightless scenes, they get about 30 seconds at a time, 30 to 40 seconds at a time. That was a big, oh yeah. And so they'd have to shoot part of a scene, and then they'd come back down. And then they'd have to shoot another part of the scene when they're doing that. And you can understand why they call it the Vomit Comet, that feeling that you get when you go over a roller coaster, roller coaster, that feeling you get in your stomach, yeah, you get that.
That's why in those space movies you'll see a lot of like
Bye, everyone.